for the last 15 years or something. And I've been applying mostly neural networks, sport quantum machines, around these topics over my research. And here today I'm a senior consultant at Closer. Closer is one of the companies that have been recruiting PhDs for working in companies. Is run by the PhD itself, João Cruz, is a PhD in physics also. So hopefully Portugal also have high-tech companies that are investing in technology to sell our knowledge abroad. Presently we are working with a bank in London. We are developing a scoring algorithm, not using neural networks but random forests, but we are doing quite well. So this is just to tell you that we can do things. We have the technology, we have the expertise, but we have to sell what we do. I think academics are always blaming about money and about not being heard, but I think they should work for it because it's possible to sell outside academia. You need some effort, some money, but it's possible, okay? And this presentation is also a little bit about business, not only from the academic side. I think it will be nice to you because I want to convince you that these technologies, it's really fantastic, and there is a lot of money to be made, not only by working in big companies like Google, as some of you are about to go in the future or not, depending on the options, but also to make your own companies. So it's never been so easy to create a startup. I've been creating my own startups. Some of them fail, other not so much. But I would like to after you finish this talk, to get really the impression that it's really possible to do amazing things with these technologies. Okay, so topics in this talk are a little overview about the connectivistic approach to artificial intelligence. There are several approaches. I've been mostly working with the neural networks. Some of my history concerning the applications over my recent works. And then I will go to deep learning. I call it revolution because it's revolutionary not only from the application side, but mostly from the concept side. It's conceptually different and conceptually very rich. Also from the applications of the deep learning. And finally, I like to have your attention to the possibilities in terms of business of these concepts. I go through some applications and some paradigm shift that is being occurring in recent years, not only from the algorithms but also from the fact that we have available much more data, and this data has been introducing a sudden shift in these models. This is a very old question of this intelligence machine. We have some examples that machines are doing amazing things like Deep Blue, where it won the chess contest, or Watson, that I think it's more impressive. I don't know if all of you are aware of Watson. I think you are, apart from the film. He won the Jeopardy contest. It's quite hard to beat, but he beat some humans. And Google, I think Google itself is some kind of a scary machine. I was talking at lunch about not only from the algorithms we have in place, but also from the amounts of data he has about us. He knows where you are, where you're searching, which emails are you exchanging with other. So it's kind of scary because it knows a lot about you, and it can even predict your actions in the future, not only for advertising but other stuff. I would not say it's intelligence, but it's something that that is close to intelligence. I think we are coming close to the levels of intelligence of animals like rats. And I will show you some examples in the end that will try to convince that we are really getting close to, especially concerning the visual cortex, the analysis of image, we are getting close to the level of animals. So I think we are getting close to that. Concerning the connectionist approach, I will put these 3 landmarks. It starts in the 40s with a pair concept that basically tells that it's possible to train an algorithm based on Hebbian learning. That is to say, after you see a cause and an effect, and you see 2 events occurring together, okay? If you see repeatedly these events, you kind of create a reinforcement, kind of create a connection between these two events, and this algorithm is sufficient to learn interesting features about the environment where this system is interacting. Unfortunately, up to the 80s, this approach was kind of just a curiosity. Nothing really useful was being done with them. But in the 80s, the multi-layer perceptron was really the first connection to machine that was really able to solve really tricky, really complex problems. And recently, with deep architectures, we have been able to really go beyond that and to get what I call it automatic feature extraction from the data and create very rich representations of the environment. Multi-layer perceptron in a nutshell, they are not able to produce rich representations. So this is a short history about the connectivity. It's a little bit of what I've mentioned before. In 68 or 69, there was an argument for Minsk that halted the progress of neural networks. He claimed that these machines were not able to do complex tasks due to several reasons. Some of them are correct, others not so much. This is a short summary about what distinguishes a connected machine from a symbolic machine. Symbolic machines are very powerful machines. We know much about them right now. They are able to process huge amounts of data very fast, but it does it sequentially, one step at a time. Okay, so they uses a very fast CPU to process the data. They are very good for very strict tests, very specific and very contained tests. But the problem is that they cannot connect all these. They have to follow strict rules. They cannot relate events that may occur at a certain time. Also, they are very prone to error. If you miss a comma in your code, you are dead. The program does not run. They are also not very energy efficient. The brain, from the other side, has a completely different approach to computational tasks. He uses parallelism instead of serial, and he uses, when he processes an image, he processes the pixels all at a time. They don't use this very fast processor. They don't have this processor in the brain, and it's also very robust. Cannot, if you damage some regions in the brain, you can also either reconstruct these connections or transfer the tasks that are performed by these damaged regions with other regions. It's also very so somehow it changes the speed by parallelism. What is a neuron? Well, I don't work too much with that. A neuron is just a unity that processes certain inputs. It sums them all together, and then it fires a signal when it reaches a certain level of activation. This has been it's well known that the visual cortex uses processes data from several layers, from the input to the upper layer where the image is recognized, and it's done that by passing signals from one layer to the other layer. So somehow it recognizes features just by passing the signals over different layers of processing units. And it can do a very complex image processing just by using this trick, by distributing computation over billions of units. So this is an artificial neuron. Its inputs. It's very important that the signal has a nonlinear transfer function. In this case, the heaviside. It can be a sigmoid. It has been noticed that this kind of function, the more nonlinear you put it, the better. So this is good for creating called sparsity of the network. It's not so good when you try to put a gradient descent algorithm, because to find the optimum in this system, you need some smooth unity. If you have very nonlinear, you end up not being so smooth, and we get problems in finding the optimum. This is the famous perceptron. It is trained. I will not bother too much with that. Just trained with back propagation or any other stochastic gradient descent algorithm. The problem is that it's very good for training regression or classification problems. The problem is that you need a lot of data to train these algorithms. You have to have, depending on the complexity of the problem, but you have to have thousands of examples in order to train this. If you don't have it, you may not bring not having enough data to constrain the optimization problem, that is finding the correct connection between all these nodes. Also, if the data is not, if your sample of the data is not well distributed over the sampling space, you may get easily problems of overfitting, or you may find trapped in local minimum. This is a very common problem for these systems. So this is just an example of fitting a function. In this case, as long as you have enough data to train a function, to train the network, you can somehow create, this is the approximation of the exact function. This is the exact function. And this is the error. So as long as you have enough training data, you end up with a reasonable good fit. Problem is that in most cases you don't have this data. You don't have, or you don't have it the way it should be. It is necessary to have for training the network. So essentially, neural network is, there are other kinds of neural networks like self-organizing maps, like essentially they are regression machines. You can train them by selecting a set of inputs and outputs, and by doing proper preprocessing, you can also find good representations of your problem. So the problem is that when dealing with problems like image processing, it is one of the hardest problems to solve. Problem is that if you don't have good features to train the network, you will not be able to train it properly just by presenting the system with pixels and the levels of color or something that you have available for the image. Okay? Why? Because pixels by itself does not give you a good representation of the image. There are, in this case, if you are trying to recognize a motorcycle, you have to have attention that what composes this element is some features like the fact that they have two wheels. Okay, the shape of the wheels, they have some shape, the distance between the wheels are somehow related to the shape of the vehicle, and they have some shapes and forms in the bike, the motor, if you don't recognize these elements, you will not be able to recognize properly a motor frame. So you have to extract features. And most of the work that we've been done in the last 20 years or something in image processing is just to find these features, okay? To graph it by hand, these features, to give to the network, and after that we can have a system that is able to recognize image with that accuracy. So neural networks can, if you have these features, you can train them with relatively easy to make some clever stuff. In this case, it's just this is a classical case of classifying objects. In this case, it's trees or animals according to the characteristics. If it has wings, it can fly. If it is big, it is green. So this is a tree for classifying these objects. Okay, by this is a pine, it's green. Is a plant, is a tree. Is a pine, is green. Okay, if it is a tree, is oak, is tall, it has leaves. So this is a classification system. So we can train our network to classify objects in the same way as children does when they are young, by looking at the relation between properties of the object, and then we can find a very simple neural network that can be used to train and to recognize and classify these objects by giving properties of the objects to the system. So after some training, you get the system to recognize properly the objects. You see that as long as you try to train more over time, the tree gets more details, so you can separate better the objects. And if you do PCA on the classifications, you can see clearly two regions. Here you cannot see very much the colors, but here is animals, and here is plants. So you can separate two kingdoms, and then in each one of these kingdoms you can separate from the plants, flower, tree, and rose, and tree, oak, and pine. These are trees, this is flowers, and also from fish to birds. Okay, so although they are not very powerful, they can nevertheless do some interesting things like non-linear mapping. In this case, if you have, for instance, this is a classical short problem. For instance, if you have two components, in this case is money and age, you can find you cannot separate these two regions by linear plans. But if you compose these two by using an even layer, you can create an hyperplane that can separate these two regions, here and here, here and here, without using linearity. Okay. So there are several problems associated with neural networks, and the fact that the recursive dimensionality is one of the worst. It means that this is local representation, so if you don't have enough training data to properly constrain your problem, you end up with several problems. One of them is overfitting. Another can be the fact that you don't have information about regions. For instance, in this case, you have two categories: the blue, the red, and the green. Okay, you try to classify a point here, and each classification can be done only. This is classified as red because it has more red data points than it has other colors. But if you end up with a region that this is two-dimensional, if you have let's say 10-dimensional, you very easily end up with regions, with squares that are not filled with data, and you cannot decide where to put what to classify this point. Okay, so you need a very large number of data points to cover all the possible situations in dimensional representation. This is one of the several most severe problems that will be solved in a way by deep learning. Deep learning one of the advantages is that it is not so much affected by the dimensional tickers because it is not looking at pixels but at pictures. Okay, it abstracts pictures from the data, and it does not need all these data points to constrain the learning. Okay, I will show you in a minute. So this is a problem of overfitting. The way to I think most of you are aware of neural networks. All of you are already, so it's I'll skip that. I think it's a problem of overfitting. All of you know that it's very hard there's problems of convergence, optimization. They can be trapped in local minimum. They are permutation invariant. It means that you don't have a mixed relation solution. And it's not always easy to find a way to determine whether your system is properly training or not. So you somehow have to craft it by hand to know where you minimize the empirical error or backgrounding or some process that may somehow avoid overfitting. This is a case where, to illustrate the optimization landscape, it means that you somehow have to use some stochasticity, otherwise it can be trapped in local minimums. It can be adding momentum or any other way to avoid these local minimums. This is just a warning sign for those that use neural networks. The problem is not the neural networks itself, it's the way you use it, you process the inputs and you understand